Hey guys, welcome to our lesson for Math 112, section 7.1, using fundamental identities. So last chapter, in chapter 6, we talked about angles and measuring their angles and measuring their trig values based off of those and what the trig functions were. And a couple times we mentioned some kind of trig identities and things like that. We talked about things like the reciprocal identity, like you see right here at the top. We talked about like a negative angle identity and some things like that. We'll kind of refresh on some of those. But what we're going to do in chapter 7 is really kind of utilize those in proving different trig identities and different trig relationships. And so it's really important to be able to be flexible in this section. For those of you who math comes as very simple, very easy, and you can kind of look at a problem, kind of understand what to do, and you do it, and bam, you're done. That may not be the case in this section. It is very, very okay to have a lot of trial and error going on in chapter 7 and beyond. A lot of what we're going to do here is going to be, you're going to see some things, and some things you may see and be like, I know what to do. I know the steps I should take. Sometimes you're going to see it and go like, I think I know the steps to take. And you're going to take them and you're going to find out that wasn't the right thing to do. Or maybe halfway through, you went a different way. And so this is something that I want you to be comfortable with struggling and know that that's just a part of the learning process. And even if I'm given a new problem, something I haven't worked through already, I struggle with it as well. Sometimes not, the initial approach may not be the right approach for that one problem. And so you may have to go back and try something different. And we'll see some of that here. And we're going to talk through it and kind of talk about some strategies. It's really about using some of the kind of key ideas and concepts that we will build up throughout these next few sections to help us figure this out. So like I said, there's negative angle identities. I want to really quickly touch on that. And so negative angle identities were things like sine of negative theta is equal to negative sine of theta. Cosine of negative theta is equal to cosine of theta. And tangent of negative theta is equal to negative tangent of theta. And then we can apply these also to our cosecant, secant, and cotangent functions. They apply exactly kind of similar to their similar functions. So cosecant is related to sine. So cosecant of negative theta would be negative cosecant of theta. Secant of negative theta is related to cosine. So secant of negative theta is secant of theta. And cotangent of negative theta is cotangent. It's negative cotangent of theta. So those are some ideas there that can kind of help us out with some of these things if we ever have negative angles, how to deal with them. Just keep that in mind in your back of your head. So first thing I want to talk about is these reciprocal identities. These are things that we've kind of talked about a little bit, right? That sine of theta is the same thing. It's equal to 1 over cosecant of theta. Cosine of theta is 1 over secant of theta. Tangent of theta is 1 over cotangent of theta. And you can apply that similarly with cosecant, secant, and cotangent, where cosecant of theta is 1 over sine of theta. Secant of theta is 1 over cosine of theta. Cotangent of theta is 1 over tangent of theta. These relationships are going to be useful in converting and changing what these trig functions are. And so what we want to do is we want to first use these reciprocal identities to rewrite these following trigonomic expressions in terms of sines and cosines. Now, notice that these are not equations. These are not trigonometric equations because there's no equals. So we call these a trigonometric expression. So looking at cotangent squared theta over cosecant squared theta, I want to rewrite this so that it's in terms of sines and cosines. And I want to do more than that. I want to simplify as well. Okay. So the first thing we do is we think, okay, well, cotangent is 1 over tangent. So that means that cotangent squared must be 1 over tangent squared. So actually, you know what? Let's do something. So that's 1 over tangent squared theta. And cosecant squared is 1 over sine squared theta. But since it's in the denominator, that's the same as just multiplying by sine squared theta, which is really nice, right? And so now I'm looking at this and I'm going, okay, cool. Well, I need to get this in terms of sines and cosines, but this doesn't help me out any. I still have this tangent. I have a sine squared, so that's nice, but that's all I got. But what we can do is we can say, oh, wait, that's right. Tangent, right? If we remember, we could write tangent of theta as sine of theta over cosine of theta. So that means 1 over tangent squared theta is really just cosine squared theta over sine squared theta. We still have our times sine squared theta. So what I did here is I did a couple things. First, I replaced our tangent squared with this sine squared. It'd be sine squared theta over cosine squared theta. But since it's 1 over that, we can flip it to get it back into our kind of nice mode like this. Okay, so we have cosine squared theta over sine squared theta times sine squared theta. Well, those cancel out, and we are left with just cosine squared theta. So that's really cool. So that means that cotangent squared theta divided by cosecant squared theta is just cosine squared theta. That's kind of cool. Now let's look over here at secant theta times tangent theta. Really similar situation. I want to start by using this tangent theta equals sine theta over cosine theta. And I want to use the reciprocal identity for secant theta. And so what I end up with is, so secant theta is 1 over cosine theta times tangent theta is sine theta over cosine theta. Now this is a fraction, so we're in terms of sine and cosine, but I don't want to just stop there. Just, right? We know that, yes, that's in terms of sine and cosine, but we need to simplify things because simple is always better. So since these are fractions, we just multiply straight across. So we multiply 1 times sine and cosine times cosine, giving us sine theta over cosine squared theta. Now that may be simpler, that may not be simpler, right? That's not too far off. It's not like over here where we had cotangent squared divided by cosecant squared, and that just all simplified to cosine squared, right? That was a really nice simplification. Whereas here, the nice simplification is that it gives us sine and cosine, which are values that we're more comfortable and easier and more easily able to identify. So this brings us to our next theorem, our next identity. So you'll hear kind of the Pythagorean theorem, the Pythagorean identity in different ways. Now, what this really relies on is, remember in the unit circle, we had that sine of theta was y and cosine of theta was x. We also had that if we had an arbitrary angle, theta, in that, let me just erase, I can't erase that. Go back. If we have some angle here, right, there's our x value or y value in the unit circle, and that's 1, right? Using the Pythagorean theorem with triangles, right, that says that, a squared plus b squared equals c squared. In this case, we have x, y, and 1, so we get that x squared plus y squared equals 1. So we can use this idea here, coupled with this idea here, to give us this formula. That's sine squared theta plus cosine squared theta equals 1. Okay, that's really cool. Make this better x. Now, from this, we can get a lot of different things. And so what I first want to do is I want to derive the kind of two alternate Pythagorean identities or Pythagorean theorems. And so we simply start with our sine squared theta plus cosine squared theta equals 1. And I'm going to divide everything by cosine squared theta. Now, you may be asking, well, hang on the left side, I can't divide each piece individually. I have to divide the whole entire side. A little side note, if we will, right? If I have A plus B over C, I can split this fraction to be A over C plus B over C. Okay, so that's why I can individually divide both the sine squared and cosine squared by cosine squared. And so when I do this, right, our sine squared divided by cosine squared becomes tangent. So we get tangent squared theta plus, and cosine squared divided by cosine squared is 1. And 1 over cosine squared is secant squared theta. So we get this other identity here. And you may be able to figure out what I'm going to do next. And that is taking our Pythagorean, our standard Pythagorean identity, cosine squared plus, or sine squared plus cosine squared equals 1. But instead of dividing by cosine, I'm going to divide by sine squared this time. And our sine squared divided by sine squared gives me 1. Cosine squared divided by sine squared thetas gives me cotangent squared theta. And 1 over sine squared gives me cosecant squared theta. So these are two more versions of the Pythagorean identity. Okay. So these are all really important things to be able to recognize and identify. Now, with these identities, we can obviously do any sort of algebra we want with them. So let's just focus on the main one. Okay, so our sine squared theta plus cosine squared theta equals 1. I could subtract cosine squared theta. Oops. Okay, all right, that cancels out. I'm left with sine squared theta equals 1 minus cosine squared theta. So the cool thing about that, and we can do an exactly similar process to give us the equation cosine squared theta equals 1 minus sine squared theta. And we can do a very similar idea with these other two identities here, right? So I could subtract 1. I get tangent squared equals secant squared minus 1. Cotangent squared equals cosecant squared minus 1. 1 is equal to cosecant theta minus cotangent theta. 1 is equal to sine squared theta minus tangent theta. Right? We can do all these different kind of iterations of these, basically isolating these expressions. We have 3 parts to these expressions, right? So this one here on the left, we have tangent squared theta as one part, we have the 1 as one part, and we have secant squared theta as one part. We can create 3 different equations from this where we isolate kind of each component on its own. And so if we look at just this over here, what this allows us to do is it allows us to do one of two things. We can either replace a cosine squared theta with a 1 minus sine squared theta, or if we have a 1 minus sine squared theta, we can replace that with a cosine squared theta. And if you notice, on the right-hand side of these two things, those are the difference of squares, which is really cool, right? So 1 minus cosine squared theta factors to be 1 plus cosine theta times 1 minus cosine theta, right? Because if I multiply these, my 1s multiply together to give me 1, and then I get a negative cosine theta and a positive cosine theta. When I add those cancel each other out. And then when I multiply the cosines, I end up with negative cosine squared theta. And so it's really useful in kind of working with all of these different things and being able to kind of recognize all of those. For those of you who just saw me factor that quickly and were like, oh my God, factoring, I hated that and it was so terrible. Yes, you are going to have to factor in this class. Yes, it will come up. Yes, it will be very beneficial to recognize, especially some of the kind of more obvious factoring things such as the difference of squares as we had here. So these are all things that we can do with just this Pythagorean identity, right? From this one identity, sine squared theta plus cosine squared theta equals 1, which all just originated from the relationship between in the unit circle and our sines and cosines, right? That's all it is. Okay, that's where this comes from. From that, we get essentially 9 different identities. So we get the originator, the sine squared theta plus cosine squared theta equals 1. But then we can also divide that whole thing by cosine to get this tangent squared theta plus 1 equals secant squared theta. We can divide the original by sine squared theta, and we get 1 plus cotangent squared theta equals cosecant squared theta. But then in all 3 of those, we can isolate for any one of the 3 components and get more equations. So each of those 3 equations has 3 components, which gives us 3 more equations. So we get 9 total equations. And you're like, oh my gosh, I have to memorize all those? No. But it's a really good idea in practice. Whenever you're simplifying or verifying or doing things like that we'll do in this chapter, when you see a trigonometric function squared, it's a very, very good idea to start thinking, ooh, Pythagorean identity is something that might be useful here. And to start looking at if that applies and how it would apply. And so looking at what you have, if you have a cotangent squared and sine squared, right, those don't fit together, right? Those equations aren't in the same set. But if you have a cotangent squared and you have a cosecant squared involved, then you'd be like, ooh, is this relatable to the Pythagorean identity or Pythagorean theorem? So you must definitely you kind of understand and be ready to utilize this, and this. It's just really good to kind of be able to recognize these guys here as well. These are all things that will be something that will be useful to you throughout the term, throughout this section, throughout this unit. So make sure you guys are comfortable with those. So let's do another example. Let's find all of the other trig functions of theta using the reciprocal identity and or the Pythagorean identity, right? All the things that we've talked about so far in this class. Given the fact that we know that secant theta is -4 and sine theta is negative. So you may ask, why do I care if sine theta is negative? You'll see in just a minute, okay? So first off, right off the bat, if we know secant theta equals -4, then we also know that cosine theta is -1/4. Now, you may be thinking, cool, so if I know cosine theta is -1/4, then I can use the idea of adjacent over hypotenuse to say that one side is 1, one side is 4, and then use Pythagorean theorem to figure out the other side and go through to all that. And that's not wrong, okay? But I want to use the reciprocal identities and or the Pythagorean identities to solve this. So I know what the cosine is, and so I'm going to use the standard Pythagorean theorem right now to say that sine squared theta plus cosine squared theta equals 1. Well, I know that cosine theta is -1/4. So cosine squared theta is just -1/4 squared. If I square that, I end up with a positive 1/16. Subtract that from both sides. I end up with sine squared theta equals 15/16. Okay, so 1 minus 1/16 leaves me with 15/16. And so now to get sine by itself, we need to square root both sides. So in square rooting both sides, right, end up with sine theta equals. Now this is where that little extra piece comes in, that sine theta is less than 0. We know that when we square root both sides of an equation, we need to get plus or minus on that other side. So if we didn't have any more information, we would get that sine theta is plus or minus the square root of 15/16. The problem is we don't really know which one it would be. But because in this problem, we're told that sine of theta is less than 0, we know that this has to be the negative version. So this means this is negative root 15/16. Now, for those of you who remember, right, when we have a root of a fraction, we can take the root of each piece. Square root of 15 is just square root of 15. It's nothing lovely. But square root of 16 is 4. So we get that sine theta is negative root 15 over 4. So let me write that over here. Sine theta, negative root 15 over 4. Whoa. Which means that cosecant of theta is negative 4 over root 15. And if you'd like, you could do negative 4 root 15 over 15. But quite frankly, this is perfectly fine here. Now, the only thing I have left is tangent and cotangent. Tangent of theta is equal to sine theta over cosine theta, as we all know. Well, sine theta is negative root 15 over 4. Cosine theta is negative 1 over 4. Negative root 15 over 4 times negative 4 over 1. Our 4's cancel, our negatives cancel, and I end up with just root 15. So tangent of theta is root 15, which means cotangent of theta is 1 over root 15, or root 15 over 15. Now, that may seem like a whole lot of stuff, right? And like, why do we have to do all of that? We could have just, we could have said, okay, x squared or a squared plus 1 squared equals 4 squared, right? And we'd end up getting that a is root 15 and go from there. And you're not wrong. But again, if I tell you on a problem, say on a test, to use the reciprocal identities to do this, I may say you must document all work, or what I would really do is I would have a few boxes where you can have some, steps to put these things in. So make sure you guys are kind of understanding this, and really don't think of this as I can do it the other way. Think of it as this is a simple problem that allows you to practice utilizing these identities and these concepts. Okay. So do the same thing with this one. We know that cotangent of theta is negative 5, and we know that sine of theta is root 6 over 3. Well, that's really cool. We've got 2 of the 6 functions already. Using the reciprocal identities, we can get 2 more. So if cotangent of theta is negative 5, that means then that tangent of theta is negative 1/5. And if we know sine of theta is root 6 over 3, we know that cosecant of theta is 3 over root 6, or 3 root 6 over 6, which simplifies nicely. I'm going to erase that because I want to simplify all at once. I don't want to take up too much room on this thing. Simplifies nicely to root 6 over 2, right? 3 root 6 over 6, 3 over 6 simplifies to 1/2. We get this. Okay, cool. How do I get cosine and secant? That's what I need. Well, to use it, there's a few different setups we can use, but let's use the fact that we know that cotangent is negative 5. So if cotangent theta, how can I relate that to cosine? Well, cotangent of theta is cosine of theta over sine of theta. So now I fill in the values we know, and we end up with the equation negative 5 equals cosine of theta over root 6 over 3. So to get this out, we multiply both sides by root 6 over 3. Root 6 over 3, those cancel, and I get that cosine of theta is negative 5 root 6 over 3. All right. Now, that's not pretty, but it is functional and works. So we have that cosine theta is negative 5 root 6 over 3. So that means that secant of theta is negative 3 over 5 root 6. If I simplify this whole process, okay, I end up with negative 6 over 10. Or sorry, negative root 6. Negative root 6 over. Stop doing triangles. Terrible 6 over 10. And there you have it. We have all of our trig functions now. Okay. So this isn't too bad, right? Utilizing these isn't too scary. Hopefully it's something that we can be comfortable with and get some practice using, and we'll definitely get practice in the homework and doing these types of problems and simplifying things. So here we need to write the trigonometric function in terms of x, then evaluate when x equals 0.5504 secant theta if sine of theta is equal to x and theta is obtuse. Whole lot of information here, whole lot of things to piece together, right? What we know is we are trying to evaluate secant theta, right? Secant theta is 1 over cosine theta, so I know I can shoot for cosine, and I can just take the reciprocal of it, and we can get our secant. So rather than trying to go, okay, I need to get from sine to cosine or sine to secant or anything like that, I can just simply get from sine to cosine and then just flip it and go from there. So what we're doing is we're going to use the Pythagorean identity, which says very simply that sine squared of theta equals, plus cosine squared theta equals 1. Now what I know is sine of theta equals x. So I know that this equation becomes just very simply x squared plus cosine squared theta equals 1. So again, we're trying to get secant, so we're trying to get cosine. So subtract our x, So we're going to subtract x squared from both sides, leaving us with cosine squared theta equals 1 minus x squared. Square root both sides, and we get that cosine theta equals the square root of 1 minus x squared. Now, is that the plus or minus version? This is where this fact is useful. Since theta is obtuse, right? So obtuse means it's an angle greater than 90, less than 180. So if we think about the unit circle, standard position angle, that means it's somewhere over here, okay? And what I know is that all of these angles have a negative cosine value. So that means this is negative. All right. So if that's cosine, that means that secant of theta is 1 over negative root 1 minus x. That's a terrible, I don't like that at all. That secant of theta is 1 over negative root 1 minus x squared. There we go. We have an expression that gives us the value of secant of theta in terms of x. Now we're told that x is 0.5504, so we can just really simply take this function. So we can look at secant of theta 1 over negative root 1 minus 0.5504 squared. Okay. And then obviously you guys know what this is, right? You can just mentally look at this and be like, done. No, not at all. I can't do that. I don't expect you to. If you can, you're probably like 7 or 8 in this class because you are a math genius. So we'll use our calculator to go through and evaluate this. And we end up getting that this is approximately negative 1.198. So we get that secant of theta is approximately negative 1.198. And one thing we can do just to make sure we didn't make an obvious mistake is think about this, right? So again, we know that theta is obtuse, so it's somewhere over here. So secant being 1 over cosine, that should be a negative number. And we know that secant and cosecant, they range from negative infinity to negative 1 and 1 to infinity. This is a value that is greater than or less than negative 1, and it's a negative value. So that checks all those kind of obvious mistake boxes. So we look at this and think, cool, that checks out. Now, function is even if, function is odd if. These are things that hopefully your 111 teacher went over with you guys. I know when I teach a 111 class, this may be something I kind of briefly go over, but we'll talk about it really quick. So the definition of these, the very kind of very math-based symbolic definitions, we say that a function is even if f of negative x is equal to f of x. So we say that even functions have a symmetry with respect to the y-axis. What that means simply is a very easy function is like x squared. Right? If we fold the graph along the y-axis, the left side falls right on top of the right side. Okay. And so that means that if we input a negative value into our function, it gives us the exact same output. Okay. And we have odd functional symmetry if f of negative x is equal to negative f of x. Okay. And we say that in this case, odd functions have symmetry with respect to the origin. Okay? The origin being that lovely point 0, 0. Okay. And so a simple function that has that is like x cubed. And so this kind of has a rotational symmetry. If we were to think about grabbing our graph and rotating it 180 degrees with the origin being a fixed point, so that's kind of being the center of it where we're rotating about, the graph would look the exact same. Okay. Now, the whole reason we care about this is those negative angle values that I talked about earlier. This is kind of where they come from. So the even symmetry functions in the trig world are cosine and secant. And all the rest are odd. So sine, cosecant, tangent, and cotangent. Okay, these are all odds. So that means for all of these, we either get f of negative x equals f of x or f of negative x equals negative f of x. Now I'm going to zoom and jump back to where we began. Since cosine has even symmetry, we can see that cosine of negative theta is cosine of theta. And since sine and tangent have odd symmetry, we get that sine of negative theta and tangent of negative theta equals negative sine theta and negative tan theta, respectively. So that's kind of where those come from. Those are kind of useful things. I wanted to kind of go over this just so that you guys could kind of see where those came from and where we're going to use them at. And so what we want to do is here we want to use even and odd identities to rewrite the following. So it's really not crazy. We just want to kind of simplify and kind of make sure that whatever's inside the argument inside of our tangent functions or our trig functions are just a singular angle value, not a negative or anything like that, just simple. So since cotangent and sine are both odd symmetry, okay, that means that cotangent of negative theta is negative cotangent, in this case we're doing x, and sine is negative sine of x. Now when I multiply negative by negative, those go away, and we end up with, let's get my equals here. We end up with just cotangent of x times sine of x. And we can do a better job simplifying this, right? What's cotangent? Cotangent is cosine over sine. So cotangent is just cosine of x over sine of x. So that's just sine of x, and those cancel out, leaving me with just cosine of x. That's cool. All right, so this kind of combines some things that use these odd and even function symmetries, giving us these kind of nice relationships. And then we also further went and used the reciprocal identity for cotangent or not the reciprocal, just the identity, the definition of cotangent there being that it's cosine over sine and simplified. So let's do it again. Now this one here has a fraction. And we're going to be adding things. And this can scare some of you guys. But let's first take care of our negative angles and get rid of that. Since secant has even identity, has even symmetry, secant of negative theta is just secant of theta. No change. Cosecant is odd, which means cosecant of negative theta is negative cosecant of theta, which means instead of this being plus, I can just make it minus cosecant of theta. Look at this. So let's see here. Secant of theta is 1 over cosine theta, and cosecant is 1 over sine theta. Now we can't just subtract these, right? It's not like 0 over cosine theta minus sine theta, right? When we are adding or subtracting fractions, we have to have that common denominator. Our lowest common denominator here is going to be the product of cosine and sine. And so what I'm going to do is I'm going to multiply on the left-hand side by sine theta over sine theta. And I'm going to multiply on the right-hand side by cosine theta over cosine theta. What that does for me is it gives me the resulting product, or the resulting equation or expression, sine theta over sine theta cosine theta minus cosine theta over sine theta cosine theta. And this can just combine into a singular fraction. Since we have a common denominator now, our denominator stays the same, sine theta cosine theta. And in our numerator, we end up with sine theta minus cosine theta. Okay, and that's it. Now, you may be really kind of thinking to yourself after this, like, all right, how is that the simplified version? How do I know when I can't simplify any further? A lot of that is just kind of experience doing these things. But a lot of it just comes with anytime you get something all in terms of sines and cosines, it'll be fairly obvious when things are going to cancel or not. Not too often are you going to have to do things where you have to kind of look at things. There's no squaring here, so there's no factoring that we could try and do. Can't pull common factors out or anything like that. It's pretty just locked in as what it is. There's really no moves we can do. No identities apply because nothing's squared. So this is as simple as it gets. Now, let's just get some more practice. That's really what this whole entire lecture is about, is getting practice applying these identities. In the next section, 7.2, we are going to verify identities. So things like we're going to be given equations. So we could be given something like cotangent negative x times sine of negative x is equal to cosecant of x, and have to verify that. And the way we do that is basically what we're doing. And we'll talk more about that in 7.2. So we need to practice doing this. Let's just look at this first one here. We have cosecant squared of x times 1 minus cosine squared of x. So we see these squares, and what should we think? We should think, that's right, Pythagorean identities. Now, I know I have one for cosecant squared, right? And if we scroll all the way back to the top, right, you can get that cosecant squared is 1 plus cotangent squared. But that doesn't really help us here. 1 plus cotangent squared, we'd end up with this big mess, and that really doesn't work. But if you remember, we did a little something with the Pythagorean identity, right? The original one where we isolated the sine and we isolated the cosine. And what we saw was that sine squared theta plus cosine squared theta equals 1. If we isolate the sine squared, we end up with sine squared theta equals 1 minus cosine squared theta. So that means that this piece right here is just sine squared theta. So what I end up with is cosecant squared of x times sine squared x. So what I can do here is I can use, very simply, the fact that cosecant squared x is 1 over sine squared x. One over sine squared x times sine squared x. Those cancel, and that's just 1. That's pretty cool. That's nice. Now what about this over here? This mess, this monstrosity. I'm just gonna give you this little skip. Okay. The reason we're gonna skip this one is it's just an unnecessary identity. It just uses the fact that if we shift things by pi over 2, what happens to these? And it's not something that I'm too worried about. I'm not going to give you any problems like this until we have some other tools in our belt to deal with. And so there's really no point in me just kind of going like, here, do this and you know, because I said so. So we'll wait until we have more tools in our belt to do that problem. Cosecant squared theta, or x minus 1 divided by cosecant x minus 1. What's really cool here is I don't need to use any trig identities to simplify this first. What I'm going to use is that numerator is, we have a squared piece and we have subtraction. So anytime we have squared and subtraction, we should think to ourselves, is this a difference of squares? And lo and behold, this is. And so what this becomes is our numerator becomes cosecant x plus 1 times cosecant x minus 1. And that's all divided by cosecant x minus 1. Lo and behold, that's gone. So I get cosecant x plus 1. What do? Well, it's always a good idea. And this is something that on the homework, I'm going to specify kind of how I want it. Most of the time I'll say to simplify and write this in terms of sines and cosines. So right here, this is pretty simplified, right? But I always want to get this in terms of sine and cosine because those are the functions that we know how to evaluate the easiest. So cosecant x is just 1 over sine x, then we have plus 1. To make this so that we can add these together, I need to multiply this 1 by sine x over sine x, giving me 1 plus sine x all over sine x. Okay. And so if you don't know what I did to get from here to here, it was very simply just adding fractions. So we ended up with 1 over sine x plus sine x over sine x. They have the same denominator, so we can just add the numerators. So we get 1 plus sine x all over sine x. All right. Part D. If I'm looking at this, I have cosine squared x times secant squared x minus cosine squared x. Again, there's a lot going on, but we see squares, so that leads us to think we might be using some Pythagorean identity or something like that. But sometimes, just as in part C, sometimes let's see if we can algebraically simplify these further. Okay, so I have cosine squared x times secant squared x minus cosine squared x. Both of these two terms, our cosine squared x, secant squared x, and our cosine squared x, have cosine squared in them. So I can factor that out. And by doing that, I end up with cosine squared x times secant squared x minus 1. Cosine squared x, we could write that as 1 minus sine squared x, but looking at the other piece, that's not really going to help us. We don't have sine in there. Secant converts over to 1 over cosine. So, I mean, like maybe that'll help, but But if we think about the other versions of the Pythagorean identity, we have some that involve secant. And if we scroll up, let's scroll up. Ooh, secant of theta, or secant squared theta equals tangent squared plus 1. But remember, we can isolate these, right? So that means that tangent squared theta equals secant squared theta minus 1. Okay, let's look back at what we have, what we're dealing with here. Well, I have secant squared x minus 1. That's just tangent squared. So using the Pythagorean identity, this piece here just becomes tangent squared x. And tangent is just sine squared over cosine squared. And that goes away, and we get sine squared x. All right. Whew, we're doing it. Now, here's a cool thing I want to show you. I'm going to do this problem again, but I'm going to do it different. So, cosine squared x, secant squared x minus, not 1, minus cosine squared x. So, like I showed, right, I wanted to talk about just doing this using algebraic methods and then using something. But let's just use the reciprocal identity on this. Well, I don't want to use the cosine reciprocal. That doesn't really help me. But I can change secant squared is 1 over cosine squared. So I have cosine squared x times 1 over cosine squared x minus cosine squared x. But if I look at this left, the cosine squared x times 1 over cosine squared x, those cancel. And I'm left with 1 minus cosine squared x. And if we remember back at the trig functions, right, when we looked at the Pythagorean identity, when we looked at the initial version, we isolated sine squared theta is equal to 1 minus cosine squared theta. So 1 minus cosine squared x is just sine squared x. And so you can see we got the same place. You may think like, well, that one took a little more, that one took a little less, right? I want to show you this, that there are multiple ways to get to the same point in different problems. You're in the same problem. So if you go one way and you're talking to a buddy and they go a different way, it doesn't mean one of you is wrong. You're both right. You may just be thinking about it differently. So that's the fun thing with these trig functions. And we are almost done. I know it seems like it's taken forever for this lesson, but these are the last 4 problems I want to do with you. And the reason I want to do this is I want to give you guys as many examples to look at, to look back to study from, so that way when you're going through the homework, you can kind of have a sense of what to do. Now, this section and these coming sections are really going to challenge your algebra skills. So things like factoring, canceling things out, adding fractions, those kind of ideas there. So if those are things that you're really weak with, be patient with yourself as you're going through these sections. And if you need to, seek out some tutoring help, either from myself or from the tutoring center, and we can make this work. So cosine to the 4th x minus 2 cosine squared x plus 1. What the heck? Right now we're dealing with to the 4th. But I want to do something here. Let's rewrite this equation. Okay, what I'm going to do is I'm going to say let's let cosine squared x equal y. So we're just going to say let cosine squared x is y. So now let's rewrite this expression. So we have cosine to the 4th x. Well, that would just be y squared. Because cosine squared x squared is cosine to the 4th. Okay, so we have y squared minus 2. Cosine squared x is just y. And then plus 1. Oh, hey, y squared minus 2y plus 1. That's easy, right? That's just a simple quadratic that we can factor. And matter of fact, it factors to just be y minus 1 times y minus 1. Because I need to find 2 numbers, right? And those 2 numbers would be these here, such that they add to be this value and they multiply to be this. So I need to find 2 numbers that add up to be negative 2 and multiply to be positive 1. And that's just negative 1 and negative 1. Awesome. Now let's replace our y again. So let's go back over here. And so there's no reason you have to replace this. This is just something that it may make it simpler for you to visualize. So I'm going to replace the y in this expression here with our cosine squared x. So what I end up with is cosine squared x minus 1 times cosine squared x minus 1. What's cosine squared x minus 1? That's almost like sine squared x, but the problem is sine squared x is 1 minus cosine. So the signs are flipped. How do I flip a sign? Okay. So if sine squared x is 1 minus cosine squared x, what if I multiply this whole side by negative 1 and I multiply this by negative 1? So if I can do that, right? I just multiply by negative 1 both sides. That's perfectly legal. So that means we get negative sine squared x equals, now our sign changes. So our 1 becomes negative, our minus cosine is positive. So we can just rewrite as cosine squared x minus 1. Ooh, that's cool. So this becomes negative sine squared x. And same here, negative sine squared x. When I multiply those together, the negatives go away, and I just end up with sine to the 4th x. All right. So that was a little bit weirder, right? But what it relied on is your ability to factor a quadratic, really, is what it boiled down to. Okay. Now, let's move on to f. Sine to the 4th x minus cosine to the 4th x. Again, we have these fourths, what in the world? But if I did kind of the same trick, right? We'd end up with, say sine squared is one variable, cosine squared is another variable. We'd have something squared minus something squared. That's the difference of squares, right? So this simplifies to be the difference of squares, which means this is just sine squared x plus cosine squared x times sine squared x minus cosine squared x. Well, sine squared x plus cosine squared x is 1. So this just leaves me with sine squared x minus cosine squared x. Okay. Now, this could be done either way. You could really flip either one. But let's say then, okay, well, sine squared is just 1 minus cosine squared x minus cosine squared x. That's just 1 minus 2 cosine squared x. Or, horrible. Or we could say this is sine squared x minus 1 minus sine squared x. Okay, and we end up with distributing this negative, so we get a negative 1, positive sign, so we get 2 sine squared x minus 1. Either way, both are perfectly fine. Notice that by switching the sign instead of the cosine, I just didn't have to do the distributing a negative, but that's pretty easy to do, so I'm not too worried for you guys. All right, part G. Oh my gosh, we have fractions. Oh no. But this is easy, right? We know how to deal with fractions. We just need a common denominator, then we add them together. I have 1 plus sine x in the denominator of 1. I have 1 minus sine x in the denominator of the other. There's no common factors or anything here. So we're just going to multiply the left side by the denominator of the right and the right side by the denominator of the left. So we're going to end up with 1 plus sine x over 1 plus sine x times 1. Oops. Let me start that over. 1 minus sine x over 1 minus sine x times 1 over 1 plus sine x. Right, so that's just multiplying the left side here by the denominator of the right side. And we have plus 1 x times 1 plus sine x or 1 plus sine x. So what this ends up becoming, if we look at the denominator, 1 minus sine x times 1 plus sine x, that ends up being the difference of squares. And so our denominator here, so we're going to have 1 minus sine x in the numerator. Our denominator is just going to be 1 minus sine squared x. 1 plus sine x, and then 1 minus sine squared x. Now, if you're not sure how that happens, it's just multiplying 1 minus sine x times 1 plus sine x. We distribute that, we end up with 1 minus sine squared x. So I'm looking at this, I have 1 minus sine x over 1 minus sine squared x plus 1 plus sine x over 1 minus sine squared x. We can simplify. Let me get my equal signs in here because those are all still relevant and applicable. Need to have those in. So when I add these, I get 1 minus sine x plus 1 plus sine x. So I have negative sine x here, I have a positive sine x here. Those are going to cancel each other out. So I just have 1 plus 1. So I end up with 2, 1 minus sine squared x. Well, 1 minus sine squared x is cosine squared x. Okay. And now, if I said to rewrite this in terms of sines or cosines, this would be as simplified as you would go. But if I said write this so that it's not in a fraction, so there's no fractions, well, then I would write this as 2 secant squared x. Because 1 over cosine squared is secant squared. Let's look at this. Not too bad. All right, guys. One more. We're almost there. Bear with me. We can do it. Secant squared of negative theta equals, or divided by cosecant squared of theta. This, if we think back to our odd and even function symmetry, this can be really easy. Secant squared of negative theta is just secant squared of theta, because secant and cosine are even symmetric functions. Secant squared of theta over cosecant squared of theta. That's easy enough. Well, secant squared is 1 over cosine squared. Okay. And cosecant squared is 1 over sine squared. And when I divide by a fraction, that's just multiplying by the reciprocal. So I have 1 over cosine squared theta times sine squared theta over 1, which is just sine squared theta over cosine squared theta. Again, if we were just saying to write this in terms of sine and cosine, this is as simple as it gets, but sine squared over cosine squared is just tangent squared theta. So this really isn't too challenging, right? This really isn't too crazy. So make sure you guys are just kind of taking your time with these, understanding that you may kind of come at it using one approach and get kind of stuck, and starting over is perfectly fine. If you have a whiteboard or lots of scratch paper, right now is the time to use it. So make sure you guys are working through that. There's one note I want to give you that will be kind of helpful on the homework. We all know, we just saw it there, that if I have a over b divided by, say, c over d, that this is just a over b times d over c, right? Divide by a fraction, we multiply by two. But what if I have something like a over b divided by c? Is there a way that I can change the multiplication, right? And absolutely, right? We just have to think of c as c over 1, right? Anytime we're dividing, it's really just multiplying by the reciprocal. even if we're divided by an integer. We just have to remember that or a non-fraction, we'll say, not necessarily an integer. We just have to remember that the denominator of a non-fraction is just 1. And so this becomes a over b times 1 over c. Okay, so this is something that will be useful on the homework that you may see and you may end up using. You may not. You may find a different way to do the problem. This is the way that I found to do it, and this is something that I think would be helpful to kind of help remind you guys of. So that's it for this lesson. I hope you guys enjoyed it. Now get going, get to the homework, and I'll see you guys later.